So as we go through that process, there's quite a number of steps involved in going through that process. And as you'll see when we actually run some of the statistical tests from next week on, it will possibly make a bit more sense when we actually have a practical example. But that's the theoretical process underlying the actual statistical testing that we're doing. That the smaller our p-value is, the less likely it is that the null hypothesis is true. Therefore, the more likely it is that we have support for our alternate hypothesis, the more likely it is that the alternate hypothesis is true. And for us to conclude that we have a statistically significant result, that means that the p-value, the probability of the null hypothesis being true, is low enough, is small enough for us to conclude that it's unlikely enough to conclude that there is support for the alternate hypothesis. The probability of the null hypothesis being true is small enough, is low enough for us to deem it sufficiently unlikely. And what that actual cutoff point is, you'll see in a couple of slides' time. It does differ from test to test and from area of research to area of research, but there are some general guidelines to help us make that decision. But it's important to keep in mind that even if we conclude that we have a statistically significant result, we never actually know if there is an effect in the population or not. We never actually know if there is an effect in the wider population from which our sample was drawn. And that's because we never have information from the entire population. All we have information from is the sample who are representative of the population. So it's important to keep in mind, even if we conclude that we have a statistically significant result, we never really know if our research hypothesis is actually true or not. All we're talking about is the probability of it being true and following certain conventions to tell us at what point the probability tells us that we have support for our alternate hypothesis. So it's important to keep in mind those caveats when we're going through this statistical testing, that we never actually know if there is an effect in the population. All we know is whether there's enough evidence for us to conclude that we likely or probably have an effect in the population. And because we never actually know if there is an effect in the population, there's a couple of different errors that we can be making through going through that process, and they're called a type 1 and a type 2 error. They're the opposite of one another, and these are two different ways that we can go wrong when we go throughout this process of statistical testing. So a type 1 error is rejecting the null hypothesis when we actually shouldn't. So concluding that we have evidence to reject the null hypothesis, concluding that we have evidence to think that there is support for the alternate hypothesis when actually an effect doesn't exist in the population, when actually the null hypothesis is true in the population. And in that instance, the effect that we see in our sample, or the relationship between variables or the difference between groups that we see in our samples, is just due to chance. It's not reflecting a real population effect. It's just due to the fact that there is sampling variability. And you can kind of think of that as if you're concluding eureka, you're saying that there is an effect, that there's something going on, when actually it isn't. The opposite of that is called a type 2 error, and a type 2 error is doing the opposite, the other way around, so not rejecting the null hypothesis when we actually should. So not thinking that we have support for the alternate hypothesis when actually an effect does exist in the population. So in this instance, our sample isn't detecting a real effect that exists in the population. And that would be kind of wiping our hands and saying there's nothing going on when we should be saying eureka, we should be saying there is an effect here. So these are two different kinds of mistakes that we can make. The problem is that we never actually know if we've made one or the other of these types of errors. We never actually know in any one particular study if we've made a type 1 error or a type 2 error. And the difficulty with that is essentially inherent to the process of doing inferential statistical testing. The reason that we're gathering data from a sample and using that to conclude about an effect in a population is because we don't know if that effect actually exists in the population or not. So the point of doing research to begin with is to try and find out something new, to try and find out something in the population that we don't already know about. But through the process of doing that, obviously we can make mistakes, and that's because the process that we go through to conclude about significance is all based on probability, and it's all based on our sample being representative of our wider population. So remember that we never actually know if there is a population effect. That's the whole point of why we're collecting data from a sample to generalize back to the population, but we never actually know what's going on back in the population. There's a few different ways we can get a better idea, and that's through the process of replicating research, doing multiple studies over and over again with different samples and seeing if we have convergent evidence about a particular effect. So I said to you before that there's a certain point that you come to when you can conclude if you have a statistically significant effect or not. As I said before, where that point is, where that cutoff point is, differs depending on what kind of test you're doing, depending on what area of research you're doing, some of which those details we'll talk about throughout the rest of the semester. But most of the time, particularly in social sciences and psychology and human sciences, that cutoff is a probability of 5% or 0.05 out of 1. So a probability of 0.05, which corresponds to a p-value of 0.05. And that's the cutoff point where if we have a 5% chance of making a type 1 error, meaning that if we have a 5% chance of rejecting the null hypothesis when actually an effect doesn't exist in the population, we as a kind of global consensus, scientific consensus, have decided that that's an okay probability of making a mistake. That's an okay probability of making an error. So if our p-value, the p-value that we get from the statistical test that we run, is 0.05 or smaller, we conclude then that we have a statistically significant effect. Therefore, we reject the null hypothesis and we proceed as if the alternate hypothesis and the research hypothesis is true. And where that point is, where that cutoff point is called our critical alpha level. And that's the critical point where we kind of move from a non-statistically significant effect to a statistically significant effect. And where that alpha is, where that critical alpha is trying to make a balance or trying to toss up the chance of making a type 1 error versus a type 2 error. As I said before, we never know if we've made any of these errors. All we can do is try and reduce the probability or the likelihood of making both of those errors. When we undertake statistical tests, there's two different kinds of tests we can do, or two different kinds of approaches we can do for any of the individual tests that we run. And these are called one-tailed tests as opposed to two-tailed tests. So I said to you earlier today and in previous lectures that alternate hypotheses tend to be non-directional. What I mean by that is alternate hypotheses tend to just state that there is a difference between the groups or there is a relationship between the variables without specifically saying what that difference is or what that relationship is. So alternate hypotheses in theory can be either directional or non-directional. In psychology, they tend to be directional though. And that's why I said to you before that for our purposes, alternate hypotheses are almost always non-directional. So an example of a directional hypothesis would be that older students perform better at statistics. Let's say that that was our particular prediction. So if we said that older students perform better at statistics, that's a directional hypothesis because it's predicting a direction that one of the groups is higher than the other group. An example of a non-directional hypothesis would be whether there is a difference in statistic performance between older and younger students. So that's an example of a non-directional hypothesis. If our alternate hypothesis is directional, then the kind of p-values that we should be computing are called one-tailed p-values that correspond to one-tailed tests. If our hypotheses, our alternate hypotheses are non-directional, then we should be using two-tailed tests. And what the one versus the two-tailed represents is the area under this normal distribution, this normal probability density curve that you can see on both the left-hand side and the right-hand side of the graph of the slide here. And it corresponds to whether we think that we want to see if there's evidence in the other direction to the direction that we predicted. And let me give you a better example of that. So in psychology, what we tend to do is that we tend to have directional research hypotheses. Remember that the research hypothesis is the prediction that comes at the end of the instruction that makes a specific prediction about a particular kind of relationship or a particular kind of group difference. But we tend to have non-directional alternate hypotheses, and therefore we use what's called two-tailed p-values, two-tailed tests. And the reason for that is that if you use a directional alternate hypothesis and therefore a one-tailed p-value, a one-tailed test, it means that you're not interested if it turns out that there is an effect in the opposite direction to what you predicted. So because of the process that we go through with this statistical hypothesis testing, if we have a directional alternate hypothesis, we can't actually see if there's any evidence for an effect in the opposite direction to what we're predicting. So to give you an example of that, let's say that we predicted that older students will perform better at statistics than younger students. Let's say that was our particular research hypothesis. If our alternate hypothesis was a directional alternate hypothesis in this instance, then we would use a one-tailed p-value, a one-tailed test, and that test would see whether older students perform better than younger students. If our data are consistent with that, then what we would do would be to reject the null hypothesis. So if in our data we see that older students do tend to perform better than younger students, we would reject the null hypothesis. But if the data don't support that, if they don't agree with that statement, we can't reject our null hypothesis, H0, but we also don't have any information about if the opposite is true, about whether younger students can perform better than older students. And in psychology, we tend to be interested, we tend to want to know if there is evidence for an effect in the opposite direction to what we predicted. So to give you a different example, let's say we were conducting a randomized control trial to see the effect of psychotherapy on chronic pain. And we predicted that psychotherapy would be beneficial to people compared to a control group, compared to a placebo therapy for people's chronic pain. If the data suggested that the opposite was true, that actually psychotherapy was more harmful for people than it was beneficial, and therefore people in the psychotherapy group had an increase in chronic pain as a result of going through the psychotherapy. If we had a one-tailed test, we actually wouldn't be able to detect that difference. We actually wouldn't be able to detect if we have an effect in the opposite direction to what we predicted. And that's potentially really damaging for us or really harmful for us because we wouldn't actually be able to see if there's evidence for the opposite thing, in this instance, the evidence of the harmful nature of psychotherapy, say. So in psychology, we generally tend to be interested if there's evidence for an effect in the opposite direction to our prediction. And that's why we have directional research hypotheses, but we have non-directional alternate hypotheses. The next slide here is just talking you through the process that we go through to undertake hypothesis testing. As I've said a couple of times already so far, this is going to be a little bit theoretical because we're not actually doing this process yet, but from next week on, it will make more sense when we actually have the practical test that we're undertaking. So the first thing we do when we're doing hypothesis testing is we decide what our critical alpha level is. We decide what our cutoff for statistical significance is. As I said to you before, that's usually an alpha of 0.05, a probability of making a type 1 error of 5%, but it sometimes does differ from test to test and from research question to research question. The next thing we do, and this is the process that we tend to use if we're using hand calculations of statistics as opposed to using a statistical package or a statistical software to help us. The thing that we do is calculate the test statistic first, and that test statistic comes from the data itself. If we're doing, say, a t-test, it comes from the difference between the two means. We then find the critical test statistic, and the critical test statistic is the value of the test statistic that corresponds to our critical alpha level. And we compare the test statistic value that we've obtained, our actual calculated test statistic, with that critical test statistic. and we see which one of those two numbers is bigger. If our obtained test statistic is bigger than or equal to our critical test statistic, we can reject the null hypothesis. And that means that the effect that we've found in our sample is bigger than the effect that we would find if there was a 5% chance of making a type 1 error. On the other hand, if the obtained test statistic, the calculated one, is smaller than the critical test statistic, we don't reject the null hypothesis, because in that instance, there isn't enough evidence, there isn't the strength of evidence to conclude that we haven't made a type 1 error. The alternate process to doing that would be, as I said before, to use some kind of statistical software like Stata, like the stats program that we've been using thus far in the semester. And we can get this statistical program to do these calculations for us. So it's a very similar kind of process. It would start off by the computer program calculating the test statistic for us. And then that test statistic would give us a certain p-value, the p-value that is associated with that test statistic that tells us the probability that we've obtained this particular test statistic if the null hypothesis is true. And then what we would do would be to compare that obtained p-value with our critical alpha level, which is our cutoff for significance. And if the p-value is smaller than or equal to our critical alpha, which most of the time is 0.05, we can then reject the null hypothesis, conclude that we have got an effect. If the p-value is bigger than that critical alpha level, we don't reject the null hypothesis. We don't have enough information to conclude that we think there's evidence for the alternate hypothesis, there's evidence for the research hypothesis. As I said before, the left-hand side is the process that we'd undertake if we're doing calculations by hand. The majority of times you won't be doing this at all because we have computer programs to do it for you. We'll be doing a little bit of that hand calculation throughout the semester just to show you the process, to show you what the computer program is doing. But in reality, if you are undertaking a research program, you wouldn't be doing this by hand. You'd be letting the computer